In Chapter 4, most of the time we're going to do is we're going to be spent practicing finding the graphs of rational functions. So I'm going to give you 3 different examples of homework type questions. The first thing that I always do is I rewrite all of my functions in factored form. So for this first one, I would get f of x. So I'm going to factor out a 5, and that would leave me with x plus 4 over x plus 4 times x minus 3. In order to come up with the sketch of a graph of a rational function, you need to find your intercepts and your asymptotes, and then use some reasoning and maybe plot additional points if necessary. So the first intercept I want to find is I want to find my y-intercept. The y-intercept is found by putting a 0 in for x. Well, if I put a 0 in here, I'm left with 20 over negative 12, which is 4 goes into there 5 times, 4 goes into there 3 times, so negative 4/3. So I have a y-intercept at 0, comma, negative 4/3. Next thing I want to do is I want to simplify this. So I have possible holes in my graph when x plus 4 is equal to 0, or when x is equal to negative 4. Okay. The other thing I now need to do is I need to identify my x-intercepts of my graph. My x-intercepts of my graph are going to be when the numerator is equal to 0. Well, when is 5 equal to 0? Never. So I have no x-intercepts. Notice if you would have figured out where your x-intercepts here before you're factoring, you would say, hey, you have an x-intercept at negative 4. But notice you're not allowed to have x equal negative 4 because you'd end up dividing by 0. So we actually know that this is at negative 4, 0. My vertical asymptotes are when the denominator is equal to 0. My denominator is equal to 0 when x is equal to 3. Then we identify whether we have oblique, horizontal, or no asymptotes by analyzing the leading coefficient over the leading term over the leading term. So if I analyze 5x over x squared, this is 5 over x. And notice this, I'm dividing by 0. So this is like the memorized in behavior of my 1 over x function. So anytime that the degree in the denominator is more than the degree in the numerator, we know we have a horizontal asymptote at 0. Now what I'm going to do is I'm going to take this information and we are going to come up with the rough sketch of this function. So I have a y-intercept at negative 4/3. So if that's negative 1, this would be negative 4/3. We know that we have a hole at negative 4, comma 0. We're going to have a hole here. That hole would have been an x-intercept, provided that wasn't there. We know we have a vertical asymptote when x equals 3. Make sure you draw your vertical asymptotes in. And we have a horizontal asymptote when y equals 0. So I have some points of information here. So now we're going to do some analysis. And I know that I have to approach this vertical asymptote either going this direction or this direction. Well, if this graph is going to approach it from this direction, I would have had an x-intercept right here in this positive range, and I don't have one. So from that piece of information, I know my graph has to go down and approach that asymptote. I also know that my graph has to come up and go through that hole, and then approach x equals 0. On the right-hand side, I can use some logic. Well, my right-hand side is either going to go like this, approaching both asymptotes. So it's either going to look like that, or it's going to look like this. Well, what I need to do is, well, I can do it a couple ways. I can plug in one number to the right of this to see whether it's positive or negative. And that will tell me which one of those two shapes I'm going to have. So I'm going to plug in a 4, substitute a 4, and I'm going to substitute a 4 into this simplified function. So I get 5 over 4 minus 3, which is 5 over 1, which is positive. And I know the right-hand side of my graph. So I got 5 over 1, which is 5. I know the right-hand side of my graph does this. So again, you want to find your intercepts, holes, and asymptotes, and then come up with a rough sketch. Again, until you get into calculus, the areas here and here where your exact values are, how big that is, you'll get that when you get into a calculus class. What we want to know is understand the general shape of these graphs. Okay, next one, factored form. X minus 6 times x plus 6 over x plus 6. First piece of information, y-intercept, put a 0 in for x, and you get negative 36 over 6, which is negative 6. Have a y-intercept at 0, comma, negative 6. Check for holes. Holes are where you have common factors in the numerator and the denominator. You are going to have a hole when x is equal to negative 6. And if you put a negative 6 into here, you're going to have a hole at negative 6/12. Next is vertical asymptotes. In the simplified form, when is your denominator equal to 0? Never. We have no vertical asymptotes. In behavior is based off of the simplified form. X squared over x simplifies to x. Well, the in behavior of this graph, x squared minus 36 over x plus 6, is going to look like x minus 6. So we have an oblique asymptote at x, or at y equals x minus 6. Really, what we have is the graph of x minus 6, except where x is equal to negative 6, we have a hole. So that graph is 1, 2, 3, 4, 5, 6. Actually, let me make it, since it's going through negative 6, so let's call that 1, 2, 3, 4, 5, negative 6. So the graph of x minus 6 has an x-intercept. Oh, x-intercepts, I forgot that. X-intercepts are when the numerator is equal to 0. When x minus 6 is equal to 0, my x-intercept is at 6, 0. So I have an x-intercept there. I have a y-intercept here. I have a hole in my graph at 6, negative 12. My graph approaches the oblique asymptote of x minus 6, and really my graph is the graph of x minus 6 with a hole in it at the coordinates negative 6, negative 12. The final function that I want to graph, 3x squared minus 8x plus 4 over 2x squared minus 3x minus 2. First thing I want to do is write it in factored form. I will let you factor these on your own, but the two factors I got were 2x plus 1 times x minus 2, except that's in the denominator. And in the numerator, I got 3x minus 2 over x minus 2. So you can check these by multiplying them together that you will get that answer. So to find the y-intercept, you put a 0 in for x. Those two terms and these two terms go away, and you're left with 4 over negative 2, which is negative 2. You have holes in your graph when you have common factors in the numerator and the denominator. I will have a hole in my graph when x equals 2. And if I put a 2 into the function, I get 6 minus 2, which is 4. I get 4 plus 1, which is 5, which is at 2 comma 4 fifths. I find my x-intercepts by setting the numerator equal to 0. I am going to have an x-intercept when x is 2/3, comma 0. I find my vertical asymptotes when the denominator is equal to 0 after simplifying. So my equation for my vertical asymptote is x equals -1/2. I identify my in behavior of this graph by analyzing the leading term over the leading term. And my in behavior is going to be similar to 3x squared over 2x squared, which simplifies to 3/2. So I have a horizontal asymptote when y equals 3/2. So I can now take all of these pieces of information and I can come up with a rough sketch of the function. Notice I'm not saying graph of the function, I'm saying sketch because we don't have intermediate information. So, plot the information I know. Let's make this one a little bigger than the last two. X, Y, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Information I know. I have a y-intercept at 0, -2. I have an x-intercept at 2/3, comma 0. I have a hole at 2 4/5, which is 1 1/5. I have a vertical asymptote at -1/2. I have a horizontal asymptote at 1 1/2. And make that hole there. And now I say we have enough information to graph this function. So first thing I know is I need to approach this vertical asymptote and this horizontal asymptote. Well, on the right-hand side, I really can't approach the vertical asymptote going up because I'd have to have another x-intercept there. So this graph approaches the vertical asymptote here. It goes here. And let's check. Yes, it has an odd multiplicity, so it crosses. It goes up and does something like this, and it approaches the horizontal asymptote. Now on the left-hand side, I can either have my graph do this, or I can have my graph do this. Well, the way to figure that out is to put a number into the function and figure out where you are on the graph. One thing I want to tell you is multiplicity also works for vertical asymptotes. If the multiplicity is even for a vertical asymptote, you're going to approach on the same side. If the multiplicity is odd, you're going to approach from opposite sides. So a shortcut you can use is figure out what the multiplicity of your vertical asymptote is. My multiplicity is odd, so I'm going to say that it's going to have to approach on opposite sides. And I would have this as the sketch of the graph of the function. Now, you can't just do a positive-negative analysis here because you're going to be approaching positive 1/2 regardless of which way you did this. Here's another reason why I knew it wasn't the negative one, the decreasing branch. In order for it to have been the decreasing branch, I would have had to have another x-intercept in this negative portion of the x-axis, and I did not have one of those. So because I didn't have those two pieces of information, I could have graphed that without even thinking about the multiplicity, but I wanted to introduce the multiplicity of the vertical asymptotes. Multiplicity of vertical asymptotes is even. They'll approach from the same side, And if it's odd, they will approach from the opposite sides.